day of this workshop. My name is Shu Watanabe, the session chair. So we have 3 talks in this session. The first talk is about strong converse bounds for compression of mixed sources states and given by Zara Kanyan. So please start your talk.
Thanks for the introduction, and also I'm thankful to the organizers for accepting my talk to this workshop. I'm going to talk about the strong converse bonds for compression of mixed states. I believe that the audience in this workshop are quite familiar with a lot of stuff, but I thought maybe it wouldn't hurt to just introduce some more background. So basically, if I want to talk about quantum data compression, it is pioneered by Schumacher. And Schumacher took the idea from Shannon's compression. Basically, Shannon defined a statistical classical source as a random variable, and then Schumacher generalized this notion to quantum version as an ensemble of pure states. So he defined a quantum source as an ensemble where pure quantum states are generated with some probability distribution. And in the setup that Schumacher considered, he considered the asymptotic version. So suppose that there are n IID copies of the source state. Each of these sequence of states are generated with product probability distribution. And these quantum states are fed into an encoder, which is a CPTP map, a general quantum operation. And these input data are mapped to some other quantum system, let's call it MN. And the goal is to minimize the dimension of the compressed information MN as much as possible. And then this data is transmitted to a decoder using a noiseless quantum channel. And this decoder wants to recover the original data with some measure of accuracy so that the output data is close as much as possible to the original data. And the figure of merit that Schumacher considered was the average error or average fidelity, which is defined as the averaging over the probability distribution for the input and output states and the fidelity between them. So essentially, the interesting variable here is the dimension of this system, compressed information Mn, and the rate of the compression is usually defined as the dimension log of dimension of system Mn over n, which is the number of the copies of the source. And Schumacher essentially proved that the optimal compression rate is equal to von Neumann entropy of the source. So we know that strong converse property holds compression. A strong converse essentially means that, so suppose that we have the optimal compression rate. And if the compression rate is just a little bit below this von Neumann entropy, then it has been shown that the error converges to 1 and it suddenly jumps to 1. So this is called the strong converse property. And first off, it was shown by Josa and Schumacher in 1994, assuming that the decoder has a specific structure, that is, the decoder can only take unitary operations, and then later fully by Winter, when the decoder can be any general quantum operation. So, okay, then the notion of quantum source later was generalized to the ensemble of mixed states. So suppose that there is an ensemble of mixed states, and if the indexes of these ensembles, the states from these ensembles are not known to the encoder, this is called the blind version. Actually, this is as opposed to the case when the encoder knows the identity of the signals from the ensemble, which is called the visible version. So blind version was studied by Koshi and Emoto, and it's been shown that the optimal compression rate is equal to von Neumann entropy of some subsystems. of system A, which is called Cauchy-Amorto decomposition. And in a visible case, it was first shown the optimal compression rate by Hordetsky as some regularization variable, and then Hayashi showed that this is actually equal to regularized entanglement of purification. So it's also worth mentioning that if we have ensemble of pure states, then it doesn't matter whether it's a visible or blind scenario. In all cases, the optimal compression rate would be equal to the von Neumann entropy, and a strong converse holds anyways. So now the question would be, if we have a compression of mixed states, does the strong converse property hold in this scenario or not? I mean that are we going to have this sudden jump in error if we go below the compression rate or not? So maybe before talking about the results in this regard, this was the question for this talk that I'm going to address. It's worth mentioning some other scenario which is very close scenario. Just there is a small difference which is called the rate distortion scenario. So suppose that we have exactly the same setup as blind and visible compression, but here instead of like having the fidelity or the error for the blocks of states, which is defined here, we compare blocks of input and output data. If we just compare each copy of the input and output data, which is called local error or per copy error, then we are not going to have this sudden jump. Actually, we are not going to have this strong converse property. And actually, we can show that, that there is a trade-off between rate and error, and we can reduce the compression rate in expense of having larger error. This has been shown in a separate work by me, Kotai Kroiba, and Debilio in a recent work. So, okay. Maybe also I can just quickly review some notions that I'm going to use. So the Rayleigh entropy is for a quantum state for alpha between 0 and infinity, excluding 1, is defined as this expression here. There are some interesting properties. The most important ones are listed here that I'm going to use. So the first off, if alpha converges to 1, it's been shown that the Rayleigh entropy converges to von Neumann entropy. The second one is that the Rayleigh entropy is bounded by the local dimension of the system. And the last one is additivity over tensor product states. For the sake of this talk, I'm going to talk only about the visible compression case because the time is very limited. So this is the setup that I'm going to remind in this slide. So we have this ensemble of mixed states fed to encoder, and the index are being seen by the encoder as well. And as I mentioned before, the optimal compression rate is equal to the regularized entanglement of purification. And by regularization, we have, I mean this quantity here. So we have some limiting quantity here. So for n convergence to infinity, if we have the entanglement of purification between an and xn, which is the classical variable of the ensemble, then the regularized version is defined here. Also I have to talk about the entanglement of purification. This quantity was defined by Terral et al. In 2002. So suppose that we have some bipartite state rho AB, and suppose that we have its purification, that is the system R is the purifying system, then the entanglement of purification is defined, suppose that by applying a CPTP map only on system R to obtain a system E, for example, in such a way that the entropy of system A and E together, or B and E together, is minimized. This is the notion of the entanglement of purification. And in order to obtain the strong converse bond, I have generalized this notion to the Rayleigh entanglement of purification. So suppose that we have still the same bipartite state and consider its purification. We have exactly the same minimization, but there is one difference, that instead of minimizing the von Neumann entropy, the Rayleigh entropy is minimized here. So still, there are important questions regarding some properties of entanglement of purification. The most important one, which is not known so far, is that whether the entanglement of purification is additive over tensor product states. And also, I also faced the same question here, whether the Rayleigh entanglement of purification is additive over tensor product states. This, if it is shown that it's additive, it's going to be very useful in many different situations. So similar to the regularized entanglement of purification, I defined the regularized Rayleigh entanglement of purification by taking into account many different copies of the state and averaging over n in the limit of n going to infinity. And I call this quantity the regularized Rayleigh entanglement of purification. So for the normal one, actually, by normal one, I mean the Rayleigh entanglement of purification and its regularization. I have shown in the paper some useful properties. So we can show actually both of them are decreasing with alpha. The normal entanglement, the Rayleigh entanglement of purification is continuous in the between 1 and infinity, and also it is continuous from right at 1. So this is quite an interesting property. Whereas for the regularized version, it's very difficult. It's not actually easy. At least I don't know how to prove it if it is continuous from right at 1. And there's many other quantities actually in information theory that the regularized version is not known to be continuous or not. And being showing continuity for this kind of expressions are very important, and there are many that they are still not known whether they are continuous or not. So this is the important open question here that I indicated in blue. And also the other point that I would like to mention is that if we can show the additivity for the Rayleigh entanglement of purification, then we can show that it is continuous with alpha, because it's going to follow from the continuity of this normal Rayleigh entanglement of purification. So this is the main theorem of this paper. So basically we can show that the average fidelity of the compression task is bounded like this, which is exponential with respect to n and this alpha quantity. And there is this regularized Rayleigh entanglement of purification. So I use this main theorem and some properties of the regularized Rayleigh entanglement of purification, such as the fact that it is decreasing and also continuous for alpha greater than 1, to show that for any rate below this limit point, the fidelity is gonna converge to 0. This is stated in this lemma. So if this was continuous, then we basically were down, and we have been able to show that the strong converse holds. But since we have this this quantity that we don't know whether it's continuous or not, there is a gap still to show that the strong converse fully holds. I mean, by fully, I mean that in the whole range between the regularized entanglement of purification and 0. However, still we can obtain this bond, and if it is continuous, then we are completely done with showing the strong converse for the visible compression. So I thought maybe it's a good idea to give some hints about how I prove this theorem. So one of the main ingredients that I use in my arguments is this lemma, which is quite old, actually, from Van Dam and Hayden from 2002. So if we have any quantum states, then we can relate their fidelity to their Rayleigh entropies as this equation, as shown here. So if beta is in this interval between 1/2 and 1, and if alpha is a function of this beta, then we can show that the fidelity is bounded like this. So this is, as I said, one of the main ingredients that I use to show the strong converse property. And the way I use it is like this. I have shortly mentioned it here. So I have the decoded states together with the environment system of the decoding CPTP map, and then I replace it with the entropy of the system itself without the decoding, the original source, and then considering some some extension of this state, then I'm going to relate the fidelity of these two states together and prove the strong converse property. So these are the steps that I'm going to explain in this slide. So this is the logout dimension of system MN is the rate of the compression, or sorry, if we have one log of this MN over N, then it's going to be rate. But however, so we have this this quantity here. We know that it is bounded below by the Rayleigh entropy, and I assume that this beta is between 1/2 and 1 in order to use the Van Damme and Hayden lemma. And then if I use just the definition of the decoding isometry, we know that the compressed information is processed by the decoder. And if I just define the decoding as the Steiner-Spring dilation of the operation D, then M is going to be mapped to some system A hat N, which is some guess or reconstructed version of the source, together with some environment system, which appears here. So, and here I basically use Van Damme and Hayden lemma. I replace this system with the original source together with another source, which is basically an extension of this state, and the fidelity of between these two states appear here. And then we know that actually if two states have some fidelity, then we can find some extensions or some purification of these two states in such a way that the fidelity of these extended systems are at least as big as the fidelity of the states themselves. So this is the Ullmann's theorem that I'm using here. And then, okay, and then let's move on to the next slide because I don't want to expand on every single step. So far we have this, the entropy of the original source together with some extension system and the average fidelity which appears in the logarithm here. And then if I take the minimum over all these extensions of this source, then we can basically show that this is equal to the Rayleigh entanglement of PP purification. So that is how we get from the Rayleigh entropy to the Rayleigh entanglement of purification. Basically is by relating the extension of the source and how minimizing the entropy to the Rayleigh entanglement of purification. Okay, so, and the final step here is that I basically rearrange all of the terms to obtain this equation that I already introduced in this theorem here. So basically after these steps, we can show that the fidelity is bounded like this. Okay, so if I want to conclude, I would say that in this work, I have studied the strong converse property for the visible compression. As I explained, the visible optimal rate in the visible compression case is equal to the entanglement of the regularized entanglement of purification. I define a new notion which is called the Rayleigh entanglement of purification and also regularized Rayleigh entanglement of purification. I mentioned that there is a big question here whether this quantity, the regularized version, is continuous at 1. If it is continuous, then the strong property, the strong converse property holds. So this is the important question that is left in this paper open. So if this equality holds, then we can show that the strong converse property holds. So the other important question that it's gonna help with many tasks in information theory is showing the additivity property. So it's not known so far whether the entanglement of purification is additive or tensor product states. Also, if we can show that this is additive for the Rayleigh entanglement of purification, then it's going to imply that this quantity here is continuous, and then we can show that the strong converse property holds. So this was for my talk, and thanks for your attention.
Okay, thank you very much for your talk. So let's, yes, Mark, please go ahead to have a question.
Hi, Zara. Thanks for your talk.
Hi.
So I have a basic question. You're evaluating the entanglement of purification for a classical quantum state, right?
Yes.
So usual entanglement measures are equal to 0 for classical quantum states, but I guess that is not the case for this quantity, right?
No, it's not equal to 0. Okay, let me just bring. Yes, here it's been shown, and no, it is not actually. It's the entanglement of purification is not equal to 0.
All right. Are there classes of states for which you can evaluate it?
So for example, for pure states, we know that the computation is very easy and it's additive and all the properties follow. But as for the other examples, actually there are some examples in some papers that they guess that it might not be additive for the mixed states in general, but other than that, I don't remember right now other examples.
Is it correct that Andreas Winter and co-authors had a paper called Additivity of Entanglement Purification Beyond Reasonable Doubt?
Yeah, that's the example I'm talking about, actually.
I see.
So they do some simulations, and basically they say that if their simulation doesn't have errors, then their numerical results show that the entanglement of purification in general, it's not additive, right?
Non-additive, okay.
It's not additive, yes.
Okay. Thank you.
You're welcome.
Okay, any questions from this? We still have a few minutes. Well, I have one question. So you said some special case like pure state case, you can compute the exponent. Is it tight in the sense that you can also show achievability for this exponential rate?
Yeah. This rate actually. So if there are some states, for example, for the pure states, we know that this quantity is additive, and then basically we can show that it is continuous with alpha going to 1. And also we know that this rate is achievable. So there is this theorem that I mentioned in the beginning. So the optimal, it's been shown actually in the early 2000s that the optimal compression rate is equal to this quantity here. So basically there are protocols that achieve these rates.
Yeah. My question is, you can achieve entanglement or purification, but I'm talking about convergence rate. When the rate is smaller than the asymptotic limit, in that case, fidelity must goes to 0. But you can also, even in that case, you can also prove achievability. So in that sense, your converse bound, is it tight in some special case? Do you know any idea?
I haven't proved anything regarding that, and as far as I know, it's not been shown. So there's not any achievability protocols for fidelity smaller than 1.
Okay. Okay. Thank you very much.
I have a question.
Oh, yes, Professor Hayashi. Yes.
So I'm slightly confused. You mentioned that you have a result in the case of pure state. Pure state means that in this slide, this rho XA is pure.
Sorry, your voice is not very clear to me. I didn't understand your question.
Maybe you should approach the microphone.
No. So I'm asking, so you are considering the pure state case, okay?
Mm-hmm.
Sometimes. So the pure state case means that this law is, in this slide, there is law, this law is pure.
Mm-hmm. So
Correct?
in the pure state case would be these ensembles that these row X's are pure.
Yes, law is pure, but I think in that case, not mixed state data compression. This is usual pure state compression. And
Mm-hmm.
in that case, the problem is already solved, including the exponent.
I see. Okay.
Mm,
Yeah.
that
For the
exponent,
pure state case,
in the
yes.
pure state case, I already derived the
Mm-hmm.
exponent.
Yes, but for mixed states, there's not any results, right?
Of course, but you write down that pure state case for that by using the entanglement of purification.
Yeah, I mean, if for the pure state case, we can simplify the entanglement of purification. It's going to be
Yes, and
equal to for Neumann entropy.
give that exponent. Strong compass exponent. Yes,
Mm-hmm.
this one is the same as my result.
Mm-hmm.
This is pure state. You also consider pure state case.
So yes, this can recover pure state case.
This is pure state
But this
case.
is just the converse part. It's not the achievability.
Yes, I know. But in my old paper, I derived that kind of strong compass exponent
Mm-hmm.
in the case of pure state. So I'm asking, this one is the same as my result in the case of pure state case.
So you are asking, sorry, can you please repeat again? I didn't understand.
So I'm asking, your this exponent is the same as my old result when the system is pure.
Okay, I see. Okay, I haven't compared it, but I think I haven't compared it explicitly in the paper. But I think yes, it's the exponent is the same. Yes. Yes, but it's a good point. I think maybe I should do it in the paper.
Okay, thank you very much. Any other question? Okay, if there is any other question, let's thank the speaker again. Thank you very much.
Thank you.
So the next speaker is Carly. Are you ready?
Yes.
Yes. Okay. Okay, just let's wait for a few minutes. Yeah, please prepare your slide.
Okay. So can you see the screen of my computer?
Yes. Can you make it full screen?
Okay.
Yeah, that's perfect. Okay, so the next talk is about tight exponential analysis for smoothing the max relative entropy and for quantum privacy amplification, and that talk will be given by Carl Lee. Okay, please start your talk.
Okay. So hello everyone. So my talk is based on joint work with my PhD student Yongshen Yao and also with Masahito Hayashi. So as a first, I will let's review the salvaged relative entropy, which will be the key quantity in the solution of the problems we talk about. And then let me introduce our exponential analysis for smoothing the mass relative entropy. And later on, I will talk about the exponential analysis for quantum privacy amplification. At last, I will give a brief summary and also some other questions. Okay, let me change pick the pointer. Yeah. So the salvaged relative entropy is defined for two quantum states, rho sigma, and also with a parameter alpha in this formula. It was introduced in these two papers independently. And as an induced quantity, the salvaged really conditional entropy for a bipartite quantum state rho AB is defined in this form. The quantum relative entropy appears as a limited case of the salvaged relative entropy when alpha goes to 1. Also, when alpha goes to infinity, then we get the max relative entropy here. We also need the purified distance. It is given as the square root of 1 minus square of the fidelity. Here, fidelity is also related to the salvaged relative entropy, with alpha being 1/2. It is well known that the salvaged relative entropy admits very nice operational interpretations. Prior to our work, it is known that it characterizes the strong covers exponents for quantum hypothesis testing for classical communication over classical quantum channels, and also for classical data cooperation with quantum-side information. Okay, let's go to the exponential analysis for smoothing the max relative entropy. The smoothed max relative entropy is defined by smoothing the max relative entropy. Here, theta rho is from a set of subnormalized quantum states whose trace can be whose trace is less or equal to 1. It can be regarded as a function of the smoothing quantity epsilon. So we for convenience we introduce its inverse function, that is the smoothing quantity as a function of the smoothed max relative entropy. The smoothed mass relative entropy is a very basic tool in the study of one-shot information theory. This is together with the information spectral relative entropy and the hypothesis scarcity relative entropy. Once more, it has an operational meaning. Wang and Weird showed that it describes in the exact way the epsilon approximate asymmetric distinguishability cost related to the two states rho and sigma. So any result on the smoothest mass relative entropy is the results for this operational problem. Okay, let's go to the asymptotics. The asymptotic equipartition property tells us that when here R is significantly bigger than the relative entropy, then the smooth quantity converges to zero exponentially. Otherwise, when R is less than the relative entropy, then the smooth quantity goes to 1. In this talk, we are concerned with the exact rate of this exponential decay. For this purpose, we derive both the upper bound. We derive the upper bound and the lower bound for the smooth quantity separately. So the upper bound is down in the sigma in the one-shot case. So we construct explicitly the subnormalized quasi-state tutor law in the definition. The construction is by introducing the P operation and also by constructing a projector. In the derivation, we have used the P inequality and as well as here the data process inequality for the sandwiched relative entropy. And the whole procedure is not difficult, it's somehow simple. So this is the one-shot upper bound for the smooth quantity. Okay, let's go to the lower bound. For the lower bound, we have to deal with the uncopies of the states. So to consider the lower bound, we need to consider any subnormalized state rho n in place of tutor law in the definition of the smooth quantity. Our method is to construct a quantum measurement and apply the monotonicity of the fidelity under quantum measurement to get an upper bound for the fidelity between uncopies of law and the state rho n. This is in terms of the measurement out, the probability of the measurement outcomes of the two measurement outcomes Pn and Qn. Here, noticed that here Pn is a information spectral quantity studied in the literature already. So we have an upper bound for the fidelity of these two states in terms of Pn being the information spectral quantity. And the upper bound for the fidelity translates to a lower bound for the purified distance, which eventually gives the lower bound for the smoothie quantity. So putting the two bounds together, we arrive here. And to get our final result, we need to deal with Pn. This is done by Marsoni and Ogawa. So the asymptoticus for Pn is given by is given here. So we get easily from these inequalities our final result. So the best rate of exponential decay of the smoothie quantity is given by here is a transform of the salvaged relative entropy with the parameter large or equal to 0. Okay, let's turn to the exponential analysis for quantum privacy amplification. So the quantum privacy amplification is a basic parameter in quantum cryptography. It can be most easily understood in this setting. Suppose that two parties, Alice and Bob, share a classical random variable x, which are perfectly correlated, means that if Alice has the value x, then Bob has the same value x. But it's correlated with adversary Eve's quantum system E, so it's not secure as a key between Alice and Bob. So we wanted to make this unsecure key perfectly secure. The way to achieve this is by perform the Hashi function on the classical random variable x. So the Hashi function is actually any function from the alphabet of x to the final key, the alphabet z of the final key. So the final state can be is expressed here. The classical variable x now turns to the classical variable z, and it is the adversarial Eve's quantum system now becomes such a form. We hope that the final state can be secure, meaning that on the z part it should be maximally mixed, while it is totally not correlated with the adversary's system, meaning that they are in the product form. And the distance between the final state and the ideal state is the measure of the performance. Here the distance can be any meaningful quantities such as the trace law distance and the purified distance, and also the relative entropy. What is this? So let's give the structure definition to the security exponent for quantum privacy amplification. So when we discuss the exponent, of course, we are dealing with the asymptotical case. So consider n copies of the state log xe, and for any hash function fn from n copies of the alphabet set x to some alphabet set zn, which is of size 2 to nr, meaning that the rate of randomness extraction is r. So apply this hash function to n copies of the raw state, we result in the resulting state is denoted by this law fn zn en. So fix the key rate, fix the randomness extraction rate, big R. Here we require that it is less than the conditional entropy of log xe. This is because it is already known. I'm sorry, I haven't cited the references. So it is known that when R is less than the relative, the conditional entropy, then asymptotically perfect randomness extraction can be approached. Otherwise, if R is larger than the conditional entropy, then the performance goes to the worst. So the security exponent under distance d is defined here. So it is the best rate of exponential decay of the performance function. It's a function of the extraction of the randomness extraction rate R. How can I? Sorry, this is something wrong. I don't know how this can be removed. Okay. Our purpose is to derive an upper bound for the security exponent. This is done by let's go to the next page first. So we are able to know about the performance function, the best performance function when it is measured by the purified distance. We can know about this using the smoothing quantity in smoothing the max relative entropy here. The basic reason is that the smoothest mean conditional entropy, which is defined using the smoothest mass relative entropy. It has a nice property that it can only decrease when a Hashi function f is applied to the classical system X. This is this also due to the form of the ideal state, we have this lower bound for the performance function. So eventually we have the lower bound for the performance of the of quantum probability amplification by the smooth quality of the max relative entropy. Because we have get the best exponent for the smooth quantity of the max relative entropy here in our main result 1. So this lower bound give us translates to upper bound of the security exponent is given by the transform of the salvaged conditional Rayleigh entropy. Our upper bound is to compare with the preceding lower bound. So Hayashi previously has this lower bound. In Hayashi's previous paper, here the distance he used the relative entropy here for the measure of the closeness, but it can be easily translated to the purified distance because we have this inequality. So it turns out that these two bounds are very similar. The only difference is here the range of t in the maximization. So this similarity and difference, when drawn on the picture, we can see very clearly. When the roundness extraction rate is bigger than a critical value given here, the two bounds coincide. So in this interval, when the roundness extraction rate is bigger than a critical value, we get the exact security exponent. But when the roundness extraction rate is lower than the critical value, the two bounds they are not the same. So in this interval, we don't know the exact security exponent. Okay. At last, I wanted to talk about a third main result. This is the security exponent measured under relative entropy or even the salvaged relative entropy. Here, if S is 0, then the bounds are measured by the relative entropy. Otherwise, it's the salvaged relative entropy of water between 1 and 2. It looks a bit complicated. I don't have time to explain the proofs. So let's simply show the result here. Okay. So we have derived the best exponents for smoothing the mass relative entropy and for quantum privacy amplification. By doing so, we provide a new type of operational interpretation for the salvaged Rayleigh divergence. This is in characterizing how fast the performance of certain quantum task approaches the perfect. Recall that previously the operational interpretation of the salvaged Rayleigh divergence is in characterizing the strong converse exponent. So this is in stark contrast. I remind that we can also see tomorrow Yongshen's talk on similar interpretations of the salvaged Rayleigh divergence. So our obtained explanation, our obtained exponent for smoothing the max relative entropy has applications in quantum information decoupling and quantum channel simulation. This will be talked in tomorrow by Yongshen Yao. We have two questions. The first one is to derive the security exponent for privacy amplification below the critical value. The second one is to find for more quantum information tasks the best exponents. This may give us opportunities to discover new quantum relative entropies. Okay, thank you very much.
Okay, thank you very much. Is there any question from the audience? So I have one question. So in your result, the conditional Rayleigh entropy appeared in the exponent of privacy amplification.
Okay,
what is the which definition do you use? I think conditional Rayleigh entropy can be there are a few choices of definition.
Yeah, it's here.
Oh, this okay.
Yes.
So you can also consider instead of rho b, consider sigma b and optimize over sigma.
Mm-hmm.
Instead of that version, you just use this version.
It turns out that this is the right version for our problem.
Okay.
Yeah.
Mm.
The solution to privacy amplification for the direct I mean, when in the case that when we discuss the performance to approach perfect is given by the solution is given by this quantity.
Okay. That's because you are using purified distance as a security metric.
Yeah, very nice question. Because we still don't know the security exponent when, for example, when it's measured by the trace distance. Yeah. So yeah, possibly for trace distance, the right version may be not this one.
Okay, I see. Thank you. Is there any other question?
I have a
Okay.
follow-up to that. So in your
Yes.
security definition, aren't you using the marginal state of the eavesdropper? Like the comparison to the ideal
Yeah,
CPP
okay.
state is uniform in the key and marginal for Eve. So shouldn't that be the reason why you get this particular
No,
version? No?
no, because in this case, I mean, the performance goes to when the performance goes to 0, then the two versions of the distance only differs by a factor of 2.
Factor 2. That's right.
So yeah. So
Okay.
there's no difference here.
Thank you.
Okay. So it's already time. So let's thank the speaker again. Thank you very much.
Okay, thank you everybody for your listening. Let me go out.
Yes.
Stop sharing of the screen. So I need some time.
Okay. So the next speaker, Jianwei Wu, are you ready?
Oh, yes.
Yes. Okay. Please prepare your slide. Okay, so the next talk is about quantum secure direct communication with private dense coding using general pre-shared quantum state, and the talk will be given by Jianwei Wu. Okay, please start.
Okay, thanks for the introduction. I will talk about the a private dense coding framework and its application in quantum secure direct communication. This work is a joint work with Masahito Hayashi. Dense coding was known as an interesting phenomenon of the quantum information. In dense coding, with the help of a shared entanglement, we can transmit at most 2-bit classical information within only one use of the quantum channel. Because we can apply the operation on only 1 qubit to transform between these 4 bare states. There are many variants of dense coding. If the pre-shared state is a general state, that means it is not necessarily maximally entangled. We also have the dense coding capacity. This is derived by Hiroshima. If the channel is noisy and infinitely maximally entangled states are available, we have the entanglement-assisted classical communication capacity. Also, the encoding ability can also be exploited from the perspective of resource theory. But here we are more interested in the security in dense coding. For example, for a maximally entangled state, 2 classical bits can be encoded into 4 orthogonal bare states. For a communication purpose, Alice should send the system A to Bob. In the worst case, the system A may be intercepted by a eavesdropper, but whichever the state was sent, it should intercept a completely mixed state. That means he knows nothing about the classical bits. So for the maximally entangled state, we have the fully security. To study the security in a more general situation, we propose the framework of private dense coding. It contains 3 elements. First, we have a general pre-shared state. In fact, it's many IID pre-shared state. Then Alice have a group of unitary operation. She can apply these operations to her share. Also, there is a noisy quantum channel connecting Alice and Bob. So we write this model as using these three elements. It is also noted that a free public noiseless channel is also available. That means they can communicate publicly and freely. With these resources, we consider two cases. In the first case, Alice apply the unitary operation to encode classical bits and send her state to Bob through the quantum channel. In this case, we have assumed that Eve does not intercept that state and allow it to go to Bob safely. However, we should also consider the worst case, that Eve can intercept the state sent by Alice through a noiseless channel. Then we define our performance in the private dense coding model. The first is the completeness. We say that a private dense coding protocol is epsilon C complete if it aborts with probability epsilon C. For the reliability, a private dense coding protocol is epsilon R reliable if the protocol aborts with probability larger than this quantity, given that Bob does not recover the message correctly. For the security, a private dense coding protocol is epsilon S secure if the information leakage of the message is less than epsilon S. Where we have measured the information leakage by this form. This is the this distribution is the uniform distribution, and this state is the final state of the protocol. Also, when we mention the private dense coding framework, it means that it is a procedure to implement communication under that model. Also, using these performance parameters, we can define the achievable rate and the capacity of our PDC model. This is a usual definition in the like the other achievable rate and capacity. To satisfy the reliability, we need to use the error verification. The error verification process includes two parts. In the pre-parts, Alice should generate a random variable y. This y is called the covering variable, and apply a universal hash function to a combination of the message and the covering variable to obtain the abstract C. And she should publicly announce the S prime and C. Then she takes this combination as the input of the encoder behind. In the post part, after Bob's decoding, he applies the same hash function on her decoding result to obtain an estimation of the abstract and compiles it with the previous abstract. If these two quantities coincide, he decides that this message is correct, or he aborts the protocol. This error verification process can provide the reliability we want. We have the this lemma obtained directly from the definition of universal hash function. It says that when applying this error verification to any communication process, if the message does not coincide, then the probability of accepting the message should be smaller enough. It is exponentially decreasing with the increase of the length of the abstract. We also should notice that some quantity are to be publicly announced. So we need to confirm that this quantity does not affect our security. So when the combination of these two quantity we denoted M prime is subject to a uniform distribution, and E prime is any quantum system correlated to it. We also need the S prime is independent of these two systems. If the universal hash function satisfies this condition, that for any fixed message M, this map between the covering variable and the abstract is bijective, then we did security of the M with respect to the whole information it can get can be bounded by the security of the communication process in the middle. We can construct a well-type channel from our private dense coding model. In the honest case, we have the channel from the classical information Alice encode to the state, to the composite state of Bob received and her share of the pre-shared state. This is the first channel, and the second channel is from the Alice encoded classical information to the state that Eve can get in the final part. In these two channels forms a classical quantum well-type channel. We should note some notations in the classical quantum well-type channel. The performance of a well-type code includes the error probability and the security. This definition is also the common definition, and we have the message rate. Intuitively, the secrecy capacity of the well-type channel depends on the gap between the capabilities of these two channels. In fact, we have this capacity formula obtained by a Divotok and Tai and Winter in 2005. We can build a detailed relation between our private dense coding protocol and the well-type code. First, for any well-type code, we have a private dense coding framework. This is constructed by simply concatenation of the error verification process and the encoder. This part is a concatenation of the decoder and the post part of the error verification. In this construction, we have the lemma that the performance of the private dense coding framework is upper bounded by the performance of the well-type code. Apart from that, we also have a converse relation that for any private dense coding framework, we can construct a well-type code. In fact, this well-type code should be assisted by public communication, but that does not matter. in the private dense coding protocol, we have a general random process from the message and the public information to the input of the wiretap channel. And we also have the output of the message from the channel output and the public information. This we can construct a encoder and decoder of wiretap code from these two general process, and this construction should satisfy this relation. It says that the performance of the wiretap code is upper bounded by the performance of private dense coding protocol. So this two relation implies a capacity equivalence of these two, of the private dense coding model and the corresponding wiretap channel. But we want to study the performance of the private dense coding model in a more practical perspective. So we will exploit a modular code construction of wiretap code. This modular construction has already been discussed in the classical case. They can easily be generalized to quantum counterpart. A modular code is as follows. Its encoder is a concatenation of inverse universal hash function and a error correction code encoder. And the decoder is some combination of the classic error correcting code POVM elements. To analyze this modular wiretap code in our model, we have to use the privacy amplification of universal hashing. This is a new result by Frederick Dupis. It says that when we apply universal hash function to a classical quantum state, and this is in fact a reduction of that result. When applying this universal hash function, we have the norm of this difference quantity. It is upper bounded by this quantity, and this is the sandwich ring conditional entropy. Using this privacy amplification lemma, we have the upper bound on our information leakage of the wiretap code. Here we provide some details of the proof. This follows by the uniform distribution of the message and the balanced condition of universal hash function. And this inequality follows directly from the universal hash lemma, and this equality use the relation between the Renyi mutual information and Renyi conditional entropy. This is a trivial by its definition. However, for this expression, this is only a one-shoot result. For the n-fold case, we need the equality that when maximizing over this input probability distribution, we have the optimization result is the same as the optimization over the one-fold case. This equality is frequently used in this type of equality is frequently used in the strong converse type theorems. So using this relation, we immediately have the upper bound obtained in this theorem. Also, for the error probability, we have the upper bound. It says that for the wild-type channel, there exists a error correcting code such that the error probability of the modular wild-type code is upper bounded by this quantity, and this is another type of Renyi mutual information. But note that this proposition is only an existence statement. If we are using a practical error correcting code, then this cannot apply. According to our previous result about the security and the error probability, we have the asymptotic achievable rate. But furthermore, if the channel if the wild-type channel are both symmetric, then the maximum is reached by uniform distribution. So we have a more direct result of the achievable rate. For the exponential decreasing rate of the for the information leakage, we hope that it decreases exponentially as the code length goes to infinity. So we define the exponent of information leakage as this. Our result shows that the exponential decreasing rate is of this form, and this form is has an improvement compared to the previous result obtained by Hayashi. However, there is also a recent result that is similar to our result, but his result can allow this input distribution to be any distribution. So in the general case, it is a better result, but we are considering a practical issue, and this result is obtained by using a random coding method. We can apply the result of modular wild-type code to our private dense coding model to obtain the bound on security and the bound on probability. But before that, we should substitute this information quantity by the model elements. So we have the lemma to simplify from the followed by the condition of encoding operation. It says that when the unitary set to encode satisfy this condition, this means that this set forms a irreducible group representation. Then the minimizer of this Renyi mutual information, the minimizer of it must be of this tensor product form. Using this property, we can write the upper bound of our private dense coding framework to in a more compact form. So we have a little summary for the code of our private dense coding framework, private dense coding protocol. The final code contains four parts. The first part is the error correcting code. And this is the redundancy of the error correcting code. And this is the message of the error correcting code. In this part, and the first part of this is the real message. And the remaining part are the covering variable and the randomness introduced by inverse universal hashing. So the rate achieved by the modular wild-type code is written as this. If the following condition is satisfied, the condition says that if the initial shared state is pure and the channel is noiseless, we have the achievable rate in this form, and this is the coherent information. How about the optimality of this asymptotic rate? Or or when does it reach the capacity? We have when the shared state is maximally correlated, the wild-type channel is a degraded wild-type channel. So this combined with the symmetric condition, we have the conclusion that this asymptotic rate reaches the capacity. We can apply this result to quantum secure direct communication to describe what is quantum secure direct communication. We will use the discrete Weyl-Heisenberg representation. This is also known as the generalized Pauli operators, but the time seems not to be sufficient, so I will skip this quickly. We have the example of quantum secure direct communication include 4 steps: the entanglement distribution, the parameter estimation, and encoding and decoding. This almost follows from the private coding protocol, but we have added the state estimation process. We can provide an efficient method for the state estimation. This method only uses the times of measurement only equals the dimension plus 1 measurements to estimate the initially shared state. So I will skip this quickly. We can substitute the estimated. We can substitute the information quantity of the private coding protocol with the estimated parameters to obtain a direct performance analysis of the quantum secure direct communication. And we also simulated the asymptotic rate and the finiteness rate in a special example. Yes, this is a result in the depolarizing channel. To summarize, we have proposed a private dense coding model to study the security of dense coding with a general pre-shared state. The capacity of the private dense coding is equal to the capacity of the corresponding wild-type channel. We have explored a modular coding method to obtain the finite code length performance and improve the exponent of the information leakage. We apply this model to quantum secure direct communication and give an efficient state estimation method for certain unknown high-dimensional states. However, there are also some issues. We did not take into consideration the statistic fluctuation of the state estimation. And in the private dense coding model, the encoding operation may be further optimized by considering a more general encoding operation. Thanks for your attention.
Okay, thank you very much. Is there any question from the audience? So I have a question. So I have some confusion about the problem formulation. So you mentioned the condition of completeness in your problem formulation, epsilon c.
Yes.
Does it mean the sender Alice might cheat and send something else instead of the valid message?
Well, no, we did not consider the case of the sender may cheat. This is only because we have the error verification process and so the protocol may abort. We are only requiring that this protocol abort with a small probability.
Yes, but you will use error correcting code, so the probability of abortion is very small if you use appropriate coding scheme, right? No. So my question is, does it affect the capacity, this completeness requirement? If you don't have any completeness requirement, then the result will be changed.
Yes, because if we does not require the completeness, then if we consider an extreme case that we did not use any error correcting code. However, with the error verification process, we can still assure the reliability.
Okay. But if you don't use error correcting code, probability of abortion will be very large, right?
Yes. Yeah.
Okay. Yeah, I still have some confusion, but okay, I have to read your paper.
Yes, we can communicate later.
Okay.
May
I also? Yeah. Sorry. Please go ahead. Sorry.
Yeah, if there is any question.
This concept comes from some cryptography. So in the case of cryptography, they prepare two concepts. One is completeness, another one is soundness. Soundness means that the result is always reliable. So soundness composes the reliability and security. So once we accept that result, so then that communication should be two security criteria. One is the reliability, and another one is this security criteria. This is soundness. And completeness means that if there is no eavesdropper, so then we can succeed communication. So succeed means that if there is no eavesdropper, we should accept that communication. So in this, so maybe this sentence somehow does not make sense, I think. So so this means that how to say, if there is no eavesdropper, then the protocol accepts communication. So aborting probability should be less than epsilon c. So this sentence forget one important information. If there is no eavesdropping, then we have this one. Can you understand?
Yeah, but eavesdropper can affect the communication between Alice and Bob.
No, there is the two situations. This is cryptography. In the case of cryptography, we need to consider two situations. One is there is no eavesdropping. For in the case of QKD, also we need to consider there is a case without eavesdropping. So in that case, we should succeed that communication. This is one requirement for QKD.
Yes.
So in this situation, we also consider that there is honest case. So we have a two situations. One is honest case. This one means that there is no eavesdropping. So in that case, we need to succeed that communication. So in the final round, we have error verification. We need to pass that result in the case of honest case.
Yeah,
but if there is another case, so if of course, and also we need another situation. Once we accept that communication, we always need to how to say guarantee that our communication should be secure. So in that case, we need the worst case. So soundness corresponds to the worst case. Even in the worst case, we need to guarantee there is no information leakage.
Yeah, but for instance, in the case of QKD, we only consider the worst case. We always assume that there exists eavesdropper, right?
No. In the case of QKD, of course, if there is no eavesdropper, only we have a noise. So in that case, we need to generate a key.
Yeah.
If in the case of QKD, we should accept that result if the noise is smaller than noise threshold, give a threshold. In that case, we need to establish that key. So in this sense, we need, in some sense, we consider honest case. In the worst case, eavesdropper get all of information. In that case, we don't need, we will not generate a key. But in the case of QKD, in some sense, we already reject the worst case. But in our setting, there's a risk. We have a worst case. In that case, still we already send information. So in that case, we need to guarantee secrecy, even in the worst case. In the worst case, if those take information perfectly. So in that case, we need to guarantee that security. This is the problem in this problem setting. But in the case of QKD, if eavesdropper takes everything, in that case, maybe we reject this one. Then we don't have a worst case.
Okay, I think I understood what you are trying to say, but the usage of completeness is a bit confusing, at least.
But this is somehow very usual. For example, if we consider that kind of computation, for example, blind computation. In the case of blind computation, we often employ that kind of concept. In the case of blind computation, if Bob is honest, then we need to accept that computation result. And also, even if once we accept that result, in that case, we need to guarantee that security. This is the soundness. But our soundness is slightly different because we need to careful about the following case. Even if we reject the result, we need to guarantee secrecy because we already send our information by using this channel. But even in that situation, we can guarantee security. So in this sense, we need to consider this one. So
Okay. Thank you very much for the explanation.
Is there still a time for question?
Yeah, this is the last talk of the session.
One.
Yes, so please go ahead.
I have one comment and one question related. So regarding literature, I guess, so first, thank you for the nice talk. And I think it's related to a previous result by Baudry, Luca Marini, Mancini, and Renner when they have a just dense coding scenario and consider security on top of it. And the other one I have with Pisarczyk and Das, Tamokna Das, where there are two receivers, like two Bobs in your scenario and one Alice. And I have a related question, what's the difference? Is it the case that the channel between Alice and Bob in your scheme is the wiretap channel, or it's a general map between what Alice sends to Bob? Because I was not sure. Or they coincide somehow.
First, you have mentioned the work of Renato Renner. Their work is about the two-way quantum key distribution, right?
True, but I think it's related in the part when Alice sends something back to Bob. I mean, because it's the same scenario that they first distribute some state, and then there's a second channel in which the security is generated. In the second step, they're generated from a pre-shared state generated in the first step, right?
Yes,
so
I think these two tasks are closely related. but I have not considered any comparison between them. Maybe there is some deep connection.
But I think, like, so back to my second part of the question is in your case, is the channel from Alice to Bob a general map, or it's a wired kind of channel, I mean, specific channel in this security scheme? Is it?
First, the channel connecting Alice and Bob is a pre-assumed channel in our privateness coding model.
Right.
Yes. So
yeah, but I mean the one that Eve does. I mean, surely Alice encodes. Yes, I agree. Alice encodes and send data to Bob. But what Eve does, is it the general map or it's some specific map like wiretap channel?
If we are considering what Eve does in this channel, we should consider the worst case, that if in the worst case, Eve can totally intercept this channel.
No, you did not answer his question. So his question is our model is wiretap or not? So of course, yes. So we employ wiretap channel model. So we have a very that specific channel WB and WE.
Right.
But there is one strange situation in the case of usual wiretap channel. WB
Yes.
and WE simultaneously realized in the real situation.
All right.
In our scenario, we mathematically define WB and WE simultaneously, but this one does not realize simultaneously. So this is a slightly different point.
So it's not equivalent to a general map, or I'm not sure I understand.
No. Of course, this is very special. We consider this special wiretap channel model.
Okay.
But
Okay.
but there is one different point from the usual wiretap channel, because in the usual wiretap channel, WB and WE simultaneously physically implemented. We assume that situation, but in our setting, physically WB and WE is not simultaneously realized.
Okay, I see.
But mathematically, in order to guarantee that requirement, it is enough to consider this model.
Okay, right. Thank you for the answer.
Okay. Any more questions? Okay. If there is no more question, let's thank the speaker again. Thank you very much.
Thanks.
Okay. So this is the end of the morning session. Thank you very much for all the
Thank you very
speakers
much.
and the audience.